Power series looks like so. We have a sum, and now we have a sub n. We had it before, not very interesting. And now we have x to the n. That is pretty much the first time we see that we have the variable x, and it can be anything, minus infinity to infinity, square root of 2, any number, inside of the series. Let's try to see what's happening. If I plug 0, the first term will be a sub 0, x to the 0. X to the 0 is 1. If I plug 1, it will be a sub 1, x to the 1. If I plug 2, a sub 2, x squared. If I plug 3, a sub 3, x cubed. And it's keep going. Do you know what this can be called? It's a polynomial. Moreover, it's an infinite polynomial. So you can write down in the chapter, we are talking about infinite polynomials finally. Infinite. Poly. I usually do poly, but this is the only time I will write down polynomials. Okay, good. Infinite polynomials. Infinite polynomials. And as you can see, let me try to tell you. If I cut this polynomial like so, that's parabola, quadratic function. If I cut it like so, that's a cubic function. If I cut it like so, that is a linear function or a constant. So infinite polynomials give us lots of freedom where we want to stop. And then that's when I'm going to tell you applications of noise cancelling headphones and other stuff. I promised to tell you today, but I will do it on Monday since there are more people on Monday. So it's a very interesting topic. By cutting these polynomials, we're going to use them in lots of applications. Sometimes n x to the 1700 is enough to the approximation of a sound. Sometimes 3 is enough. This one centered at 0. Centered at 0. So I will show you when it's not centered at 0. That's a second one. Bullet point, bullet point. The second one has a shifted center. So we're going to call C sub n terms, coefficients. And then we're going to have x minus a to the n, where a is a center, starting from 0 to infinity. Make sure you have enough space, because that will take more space. The first term, when I plug 0, is C sub 0. C sub 0. Plus, now we have C sub 1 and a shift x minus a. Plus, C sub 2 and we have a shift x minus a squared. And it's keep going. It's an infinite polynomial, but this time centered at a. Centered at a. Let me show you that. A is this shift we see. And also, the most important part is that now we're working with x. That is pretty cool. Now we have x. As you can see now, all those a sub n's are coefficients, right? They're constants. X is a variable, like it always was. Or we also have a shift if it's centered at a. Notation is not very smart. The book is not very smart about this. It uses a sub n as coefficients for the first series notation, and then it uses as a center for the second one. Not very smart, and I just did not like it, but let's stick to the book so you'll not be surprised. This is a definition. Let's put it in the rainbow box, all of this. That's a fat looking box. Nice. Oh, very pretty. Very pretty. Kind of like it. Good. See how nice it is? Look at this. How pretty. It changes color while I'm like drawing it. I like it. Now, let's actually discuss some definitions. We're going to define convergence test. You see, I'm using green color. When I was a student, I was color coding all my math classes, and green was for the definitions. I liked it. Red was for theorems, black examples, blue properties. And then before the exam, I would scroll really fast, and I would see the important stuff. So color coding is a really cool method. I highly recommend. So convergence set is a set, guess what, where the power converges. Like, not very creative. A set on which power series converges, converges. Example, so let me show you the sketch, and then I'll show you some 3 types of convergence sets. Basically, convergence set is a safe space. That's how I try to rephrase it sometimes. Convergence set always has A in it. That's a center. Let's call the center, center A. And then how far you can step away from A to keep the convergence. Convergence set is where the series is safe. Again, if we're approximating explosions, everything will explode and blow up when the series diverges. Sound systems, they go and get too noisy, and now we cannot take them into account when it is diverges. So we need to know where it is safe to work on. Convergence set is a safe space. There we're going to teach you how to differentiate series, integrate series, that's next week, and do other stuff, find maximum, minimum, and code it in R and Python, and then do lots of cool stuff in applications. All of this can be done only when the series converges, when it is peaceful, so it doesn't blow up. That's kind of the intuitive idea. Convergence tests have a step size. Where is it safe? Maybe like so, step to the right and step to the left. It's always the same step, so we're going to call it R. R is the radius of convergence. Radius. So that's going to be your next homework and exam, to find the radius of convergence. So let me write it down. R is radius of convergence. A is a center. So those are 2 things you'll be asked to find again and again. And we're going to have 3 cases. So first of all, let me make a very important note. Put a semicolon and say, it always series always converges at the center. Series always converges at the center A. So at A. Why? So here's a series at the very top. Why it always converges at A? For now, it sounds like a very stupid theory, which is very theoretical theory, but actually has lots of applications, and it's pretty clever. If I plug A into this series, I will have zeros all the way. See? I'll have 0, 0, 0, except the very first term. So the series converges to the finite number. That's why at center it always converges. If I plug center here, then I'm literally plugging 0 everywhere. 0, 0, 0, 0, 0. A sub 0 is the only number left, converges to a finite number. And we even know what number, the first term. So series always converges at A. So let's do that. We're going to have cases of a convergence set. So convergence sets. Let's see what is happening. We might have just A, a center. The series might be so mean that it only safe at the center. The moment you step away from the center, it blows up. Even if a step size is super tiny, 0.0001, step away, everything blows up. The second case, it maybe converges everywhere, minus infinity to infinity. Converges everywhere, everywhere. That's pretty cool. Some series are safe everywhere. All real numbers. Finally, it can be an interval. Interval is a complicated case because now it has different cases. Open interval, semi-open interval on one side, or another side. For this one, we actually have to check the ends. Check the ends. Because we don't know, well, we have to check to include ends or not. Check the ends, exclamation mark. Let me tell you the radius of convergence for each case. When I show you examples, it becomes very clear, I promise. For each case. So, the last one is the most clear. For the last one, Radius is just r. R can be some number. It can be 5. It's not going to be a negative number. R is a positive number. It can be 0.7. That's basically a step size. Again, you see how I show it here? R is my step size. How far I can go to the right and to the left to stay safe. Guess what is R for the second case? What is the safe step size for the second case? Infinity, not 0. Infinity. Since it's safe everywhere, I can go as far to the right as I want and as far to the left as I want on the x-axis. And for the first one, you actually were right. The first one is 0. The no step size is allowed. No step away from the center is allowed. That is the radius of convergence. What do you think about this? Does it make sense or a little bit confusing because it's new? Don't touch that. Now, how can I check the time? Okay, good. Not too bad. I will show you examples. I think you will like it more with examples. So, we had this example before, actually. Maybe you remember. Do you remember this example with x we had before in some homework? Do you remember? Yeah, anyway, let me show the example. Example 1. We had before the sum 13x minus 7 to the n. Don't you remember this? We even did it in office hours together. That was a geometric series, and they ask you to figure out for what x it will converge. So, let me write it down. This is geometric series. It's also shifted. Let's call it correctly. It's also a power series. So geometric series can be also a power series. Power series. Why it's a power series? Because we have a known inside, like so. It's an infinite polynomial. Centered. That's not D. Centered. What is wrong today? Centered. Yes. No? Centered. No, that's good. At 7. So A is 7. Let me write it down. A is 7. Well, now it's also, the A notation is so lame. Let's not put it A. Because now we have A for geometric series, if you remember the first term. Let's just put 7. Centered at 7. So it's shifted. It's shifted series. Let's see. Geometric series solution. The question is, find the convergence set. Determine the convergence set. Determine the convergence set. That's going to be the question for the rest of the chapter, to be honest. Solution. I know that it is a geometric series. So what is my R? Who knows? Whatever is inside of those parentheses with n, that's always your R. Because R is a common ratio, so. X minus 7, exactly. That's my common ratio. Remember, geometric series converges when? So in order, let me put it back in black. In order for geometric series to converge, R by absolute value, which is x minus 7 absolute value, must be less than 1. We did this before in the homework. That was a very first introduction to power series without mentioning it. So you solve for x, and that gives you a safe space. And also interesting, geometric series must be strictly less than 1, so we don't have to check the ends of the interval we're going to receive. Let's solve for the x. X minus 7 is from minus 1 and 1. Add 7 to both sides. X will be between 1 plus 7 is 8. Minus 1 plus 7 is 6. That is the convergence set. Check this out. So, very interesting. Convergence set. I will introduce new terminology to you right now, and that's why this example is so important. Answer. Your homework will ask these questions. Convergence set is not written as inequalities. It's written usually as the intervals from 6 to 8. And we do not include endpoints because we know that geometric series requires absolute value to be less than 1, strictly less than 1. So we know that. Now, what is your radius and what is the center? Convergence set is given. Now we want a center and we want a radius. That's what you'll be asked all the time. The center I already mentioned. Did you see it before? 7. Whatever is the shift is, that is your center. Let me write it down. Center is over here. Center is 7. So it's centered at 7. A equals 7. What is the radius? 1. How do you know? Oh, interesting. So actually you see how the center works. This is how I also do it. And then I learned the better way to do it. So let's sketch the graph or sketch the diagram of that situation. This is my x-axis, right? So this is x-axis. The center is 7. Then we found the convergence set. It looks like this in blue. From 6 to 8, we have a safe space. The moment we go outside of 8, for example, like 8.1, the series blows up. We cannot differentiate it, integrate it. Everything goes wrong. The moment we go outside of 6, the same thing. What is the step size between those 2 points? From 6 to 7, you have what? 1. From 7 to 8, you have what? 1. This is the way you can detect the radius of convergence. Let me review it again. It's called radius of convergence. They also call it set of convergence, but actually mostly known term is convergence set, and it's faster to say. The other way to see the radius is from this notation, r is 1. The moment you set x minus 7 to be less than 1 by absolute value, that tells you the step right away. Moreover, it tells you the step and the center, like so, right away. So from this first, this is the most important part. From this notation, it tells you everything. It tells you everything you need to know. Ask me, does it make sense? What do you think? Yes? No, that's actually very rare. We're going to ditch the metric series for a while. But because we taught you those and tortured you with those in the exam, it makes sense to also talk about them and then move on. But yeah, good question, good job. Unfortunately, after your question, I actually have to summarize what I just said about geometric series. And then we're going to move on to other stuff. So the question was, are they all geometric series? Yeah, the answer is no. Geometric series. Let's summarize the knowledge of geometric series we learned and attach this knowledge to new information, which we're going to call power series. Ax to the n, a plus, ax plus, ax squared plus, and so on. And it's from 0 to infinity. We're going to have here, it all converges for absolute value of x less than 1. And we even know it converges to what? It converges to s, a over 1 minus r. So in this case, it's x. A is not the center. That's the unfortunate miscommunication between notation. That's the first term. First term. That's what we did. Let me put it like so. A is the first term. Interval of convergence is interval of convergence is from -1 to 1. That's when there's no shift. We did geometric series with a shift. Interval. Radius is 1, center 0. That's if there's no shift. And it looks like so. Centered at 0, because if I plug 0, everything becomes 0 except the first term A. Then this interval of convergence, that's my safe place, is from -1 to 1. Do not include endpoints. The radius is 1 because it's a step size. Centered at 0. The one we did before was geometric series with the shift. With the shift. That's to summarize the geometric series. And to be honest, we're going to teach them for a while. So you will have a couple examples, but I don't even remember including them on a test anymore. I think it was enough to have them on a test before. There are much more other interesting series to talk about, and I can give you last example for today. I think it's like too overwhelming to do too many examples. Last example, perfect for 5 minutes left. Check this out. And that's the most important example for this chapter because now you can do all the homework. Check it out. The sum 2x to the n over n to the 6. N is from 1 to infinity. Find the convergence set. Find or determine the convergence set radius center. Like so. Pretty cool. Solution. Well, actually, center is 0. The moment you don't see a shift, you know the answer. But convergence set, that's not geometric series anymore. So this is power series. We see it's not geometric series anymore. We're going to do the ratio test. And the ratio test will always be your friend for this semester. The ratio test says, let's find the limit, and I will not write down too many things anymore since we're getting so good at this. Plug n plus 1, everywhere you see n, don't touch x. 2x, I will color code, n plus 1, over n plus 1 to the 6. Absolute value. Multiply, copy, but flip the order, numerator and denominator. Too fast or you got it? Because that's kind of the previous material. Too fast, let me know. Or it's not too bad. Now, all this stuff we did before, keep following the same way. Collect the terms that look alike, and then simplify as much as possible. Check this out. I will collect x's on top of each other, just to see how it looks. 2x to the n plus 1 and 2x to the n. Then I will collect n's, n to the 6, n plus 1 to the 6. Let's simplify x's. There's a song about this, x's and o's. You should Google this. So 2x n plus 1 over 2x to the n. What is that? 2x, right? Check your power knowledge of exponents. So that is correct. And now, very interesting situation. This is the first time maybe I will show you before calculus 3 starts. Multivariable situation, we're going to do in the integrals and derivatives, but right now in the limit. I see two variables. X is a variable and n is a variable. For this specific limit, one of them is not a variable. That's interesting. We do know that x is changing and n is changing. N goes to infinity, x can be anything you want. But for the limit, this piece is a constant, so I can kick it out of the limit. Did you have a question? Yes, exactly. Good job. In calculus 3, I'm going to do partial derivatives. This, in this case, limits, partial limits, and we're going to do partial integration in calculus 3. That's why it's called multivariable calculus, because we will have several variables in one situation. I'm kicking out 2x outside of the limit because limit cares only about n. Let me put it in some kind of amazing blue color. N. N is moving. X is not moving when you talk about the limit. So you only need to find this limit. And you don't need absolute value for n, but there is a mistake here. Did you notice? Absolute value has to be with x as well. You cannot kick out 2x outside of absolute value because we require x to be non-negative. So that's what absolute value is doing here. What is the answer for the limit? times what? Who knows what is the answer? So actually, I don't want to keep writing this limit because too messy, and n is not going to be negative anyways. What is this limit? 1. Take the leader of the top, take the leader of the bottom. They have the same power. The answer will be the ratio of leading coefficient, which is 1. So now you have this situation, 2x times 1. We almost have the answer. Guess what is the next step? That should be less than 1 for the ratio test to work. Ratio test says by the ratio test, L must be less than 1 in order to converge. And if that happens, we even say it converges absolutely, which means by absolute values. So I will enforce this. Then solve for which x absolute value of 2x times 1 will be less than 1. Does it make sense? We will check for which x we're going to stay on the safe interval of convergence. It depends on the input. If x is 1 million, for sure that's not going to be less than 1. But there are some x's when it works. 2x is between -1 and 1. Divide by 2. Since we're dividing by the positive number, we don't change limits of signs of inequalities. X is from -1/2 to 1/2. And that is the interval of convergence. Too fast or no? What do you think? Let me know. And someone says easy. Well, okay, maybe not for everyone. So let me know if it's too fast. Answer. We're asked 3 things. Thing number 1 is convergence set. Convergence set will be an interval from -1/2 to 1/2. Make sense? Step 2. Second thing we asked about the radius, and third about the center. Let's call it A. On the exam, I will call it A anyways. What is the radius? Kind of obvious. 1/2. Radius is a step size. Maybe I should write down once. Step size. This is my safe step size, 1/2. And what is the center? 0. If you don't understand that, because it's new material, don't be bothered too much. It comes later. Very natural. It was at 0 right away because there was no shift. And then we learned that the convergence set is from -1/2 to 1/2. So what is the step size? The radius is 1/2 to the left and to the right. However, unlike in the previous example, we actually need to check the end points. So note, you're actually supposed to check end points. Check end points, which are what is happening at 1/2 and what is happening at -1/2. So one can converge, for example. Then we will include one of those. Maybe both give us convergence. Then we're going to include both. Luckily for you, in this class, we don't require you to check the ends. That is actually pretty challenging because you will use other knowledge like geometric series and other stuff like that. In this class, somehow they skip it. You will see in your homework they only ask you for the open interval, which means they skip checking the endpoints. But I will always explain it just in case. Good job, people. That's how you can start your homework now. You can finish 8.4 and start 8.5 today. Both are pretty time-consuming, but one is due Monday. The other one is due, I don't know. I should check. Wednesday? Should I make it Wednesday?
No. Please no.